Welcome to lecture 3 of design and analysis of algorithms. Here we will discuss asymptotic analysis. So why we care about asymptotic analysis in algorithm? So the goal of asymptotic analysis is to find a bound or an asymptote, of a function fn. That fn can denote algorithm's time complexity or space complexity, whatever. The meaning is that fn tries to find another function gn which approximates fn at higher values of n, where gn is called asymptotic curve or asymptote of fn. So we can use asymptotic notations such as big O, big omega, theta to describe the asymptotic running time of an algorithm. So the first asymptotic analysis we'll study, this is big O, very important. Big O helps us to find upper bound. So let's say two positive functions fn and gn, fn greater than 0, gn greater than 0. Both are positive functions. And for any constant c greater than 0, any input size n naught in n naught is an instance of n. So here we can see in this diagram. So this side in the x-axis n is there, n is the input, and n naught is any instance of n. Now if fn less or equal than c into gn for all values of n greater than equal to n naught, then we can say that fn is equal to big O of gn. Means here the meaning is that the function fn grows no faster than gn. Here you can see this side y-axis growth rate, and here is the in the x-axis n is the input side. Here after this point n naught, always the growth rate of c into gn is more than the growth rate of fn. Means what? Fn finds another function gn which can approximate fn at higher values of n. So that's why we will say that gn is the asymptote of fn. So, but you see, one important thing is that from here to here up to n naught, for smaller values of n, let's say, anything can happen. Like here, sometimes c into gn's growth rate is more than the growth rate of fn. Sometimes the growth rate of fn is more than c into gn. So we should not analyze for smaller values of input. We should analyze for larger values. That's why we will always consider from this point and not to infinity here in this side. So the first question here is that is 2 to the power n plus 1 equal to big O of 2 to the power n? The notation for big O is this capital O. So here we can also say order. Okay. So from order it comes like, order, the first letter is O. Okay. So the question is 2 to the power n plus 1 equal to big O of 2 to the power n? So we need to check it. So to check it, we need to do what? Here it is clearly written that if fn is less or equal than c into gn for all values of n greater than equal to n naught. What is n naught? N naught is an instance of n. So for all values of n greater than equal to n naught, if this equation holds, then we can say that fn is equal to big O of gn. Now we'll find out similar things here. Now if I say that 2 to the power n plus 1 is equal to big O of 2 to the power n, then by definition we should go by definition. So by definition 2 to the power n plus 1 should be less or equal than any constant c into 2 to the power n. So now here you see in place of fn, we can think 2 to the power n plus 1, and in place of gn, we can think about 2 to the power n. Now, if we can show that this equation is true for all values of n greater than equal to some n naught, then we can write that 2 to the power n plus 1 equal to big of 2 to the power n. Now here you see, if we break it, so 2 to the power n plus 1 is nothing but 2 to the power n into 2. So this is less or equal than, so if I say the value of c, let's say for example, let's say I'm going to put the value of c as 2. So 2 into 2 to the power n. Now you will see that this equation is true for all value of n greater than equal to 1. So here the value of n naught is nothing but 1. Now you see, you can try different values of c here, then accordingly you will change n naught. Okay, so but this is true. Yes, this is true. You see, this is true for n equal to 1. For n equal to 2 also it will be true. N equal to 3, n equal to 4. So it will be true for all values of n. So we can say that yes, Fn. So here you see Fn is what? 2 to the power n plus 1. So this is equal to big of Gn. Gn is what? 2 to the power n. So we need to only find the value of C and n naught. Okay. So this is the concept of big O. Okay. Always go with the definition. This is the most important thing. Fn less or equal than C into Gn, and always try to put the value of n greater than equal to some n naught. You need to find out the n naught. Okay. Then we'll move to the next example. So here they are saying that, okay, in example 1, it is said that to find upper bound for Fn. Fn is given 3n square plus 2n plus 3. So here if I find upper bound, means what? I need to express it in terms of big O. Okay. So okay, 3n square, I will write 3n square plus 2n plus 3. This Fn should be less or equal than some C into Gn. Now in this case we do not know Gn, right? So let's say the highest power of Fn, so highest power of Fn, this is n square, okay? Highest order term. So here let's say I am writing the value of Gn here. Gn, in place of Gn I am writing n square. Now I need to show this thing that it is true for all values of n greater than equal to some n naught. Now I can do one thing. Here this equation will be true, 3n square plus 2n plus 3 will be less or equal than, I can write anything here. I can write anything here that will satisfy the equation. Let's say I'm just adding up this uh, coefficients. So 3 plus 2 plus 3, so it is 8. So let's say 8 I am writing here into n square. Okay. So now if I write the value of C as 8, now it will be true for n greater than equal to n naught. Let's say here it is, you see, 1. So for 1 also it is true, for 2 also true, 3, 4, 5, 6, so it will be true for all value of n. Now if this equation satisfies, then we can say that Fn is equal to big of Gn. Now what is our Gn? So Gn here we found Gn is n square. What is C? C here is 8. What is n naught? N naught is 1. What is Fn? This thing is, entire thing is Fn. Okay. So if Fn is less or equal than C into Gn for all value of n greater than equal to n naught, we can write what? Fn is equal to big of Gn. So in this case, we can write Fn. So Fn is nothing but 3n square plus 2n plus 3. So this is equal to big O of Gn. The value of Gn is what? So here we found the term Gn as big O of n square. So the upper bound that I find for this Fn, that is big of n square. Now you see, very interesting thing. So here, let's say I am going to put different values of C. Let's say 3n square plus 2n plus 3. Can I write like that? C 3n square plus 2n plus 3 is less or equal than any c. So let's say, for example, I'm going to write the value of c as 4. Okay. So for that thing also it will be true that 4n square. So but then for all value of n should be greater than equal to. So you need to find out the value of n. So in that case, the value of n not will be 3. So if I write n, the value of n naught as 3, that will also satisfy this equation. So in that case, I will write 3n square plus 2n plus 3 is equal to big of n square. But where you see the value of c is 4, the value of gn is n square, and this is fn. Now, can I change the value of gn? Yes, I can do that also. You see, if this thing is true, 3n square plus 2n plus 3 is true for n square, I mean, it will be true for n cube also, because n cube is greater than n square. Yes. So, can I write like that? So, here if I want to write that 3n square plus 2n plus 3 is less or equal than, let's say, again I am writing here 8. So 8n cube. If I write cube, then also it will be true for all value of n greater than equal to 1. Right? Means I can write any term here that is greater than or equal to the highest order term here, excluding the coefficient. So in that case, I can write 3n square plus 2n plus 3 will be equal to big of n cube, because gn is now n cube. Okay, the value of c is what? The value of c is 8. Is it true? Yes, it is also true. It is correct. Is it correct? Yes, it is also correct. Is it correct? Yes, it is also correct. But we should always go with the closest one, right? Closest one possible. So here closest one possible is what? The closest one possible is n square. So value of gn here we should take, that is n square. Now, very important point I'm going to discuss here. So here just please concentrate. So here I will discuss the important point. If I am saying that f of n is equal to big O, if I write, so you see here you can write any term that is equal to fn or greater than fn. I can write anything here that is equal to or greater than fn. Now let's say, for example, if I say that n is equal to big of n, is it correct? Yes, it is correct. Now if I say that n equal to big of n square, is it correct? Yes, it is correct, because here you can write any term that will be uh, equal to or greater than fn. So here let's say it is fn. So big of something you will write that will be equal to or greater than fn. So this is right. But can I write this one? N equal to big of, let's say, log n. No, I cannot write this. This is not correct, because here you see log n is not greater than n, log n is not equal to n. That's why I can write. Okay, so this is the uh, concept of finding upper bound. Okay, now another example here. Given fn equal to 3n square minus 100n plus 6, find gn c which will be greater than 0 and n naught, for which fn is equal to big of gn. Now they said that already, that fn is equal to big of gn. So if fn is equal to big of gn, then we can write what? Fn less or equal than c into gn for all value of n greater than equal to some n naught. Now what is fn? Fn is given 3n square minus 100n plus 6 less or equal than some constant. So here let's say, for example, I am writing 3. 3, and I am writing, let's say, highest order term, n square. Okay. So is this true for all value of n greater than equal to 1? Okay. Yes, it is true, because you see something is getting subtracted here from 3n square, but here we are not going to subtract anything. So for large value of n, okay, so this term will be less or equal than 3n square. So what is the value of c? The value of c is 3. What is gn? So gn is what? N square. And what is n naught? N naught is 1, because from this point onwards this equation will be always true. So this is Fn, right? So this is our Fn. So Fn is less or equal than c into Gn for all value of n greater than equal to some value n naught we found 1. So we can write what? Fn is equal to big of Gn, right? So if this is if this is true, this equation is true, then we will find the value of Gn, C, and n naught. You see, the Cn is what? Okay, Gn is what? N square. What is the value of C? 3, that is greater than 0, yes. And what is the value of n naught? N naught is 1. So this is how we need to solve. We need to find out upper bound, and we need to solve the questions related to uh, upper bound or big bound. Let's look at the next asymptotic notation, that is big omega, that is lower bound. Okay. So we have already seen upper bound. Now we will see lower bound. Same thing, just opposite to that thing. I mean, just the sign will be changed. For two positive function fn and gn, and for any constant c greater than 0, any input size n naught in n, if f of n greater than equal to c into gn. Now here in this case, fn is greater than equal to c into gn for all value of n greater than equal to n naught, then we will say that fn is equal to big omega of Gn. Means it is going to find lower bound. Here you see in this curve, if you see after this point, okay, n naught, always the growth rate of Fn is greater than equal to Gn. Okay. So the example here is to find out the lower bound for this Fn. Same example I have taken. I will write 3n square plus 2n plus 3 greater than equal to, let's say here I am writing the highest order term for Gn, and 1 is the value of C. Can I write it, and is it true for all value of n greater than equal to 1? Yes, it is true. Why? You see, 3n square plus 2n plus 3, if you put the value of n as 1, you will see that this left hand side term, this is greater than equal to the right hand side term, right? And it is true for n equal to 2, 3, 4, 5, 6, okay, any value from this point. So what is the value of n naught? N naught here is 1. What is Gn? Gn is n square. What is C? C is 1. What is Fn? So here this is our given Fn. Okay. Now Fn is greater than equal to some C into Gn for all value of n greater than equal to 1. So 1 is the value of n naught. Okay. So can we write f of n? F of n, that is given to us 3n square plus 2n plus 3. This is equal to big O of Gn. What is Gn? Gn is n square. So here I can write, okay. So not big O. So here it is big omega. Okay. So big omega of n square. Okay. So 3n square plus 2n plus 3 equal to big omega of n square. Okay. So here in place of this n square, can I write the greater values like n cube, n to the power 4, like that? No, I cannot write. But yeah, I can write lower order terms. Yes. So how can I write lower order terms there? So let's say now 3n square plus 2n plus 3 is greater than equal to, let's say 1 into n. I'm writing lower term. For all value of n greater than equal to n naught. N naught is, let's say, 1. Okay. You can change this value c and n naught. Accordingly, you need to change, you need to check the equation. Now here also it is 2. So can I write 3n square plus 2n plus 3 is equal to big omega of n? Yes, I can write. So in the earlier case, we found that, okay, 3n square plus 2n plus 3 is equal to big omega of n square. Now we are observing that it is big omega of n. So yes, both are correct. Why? Here the important point for big omega, that is, here you see Fn is equal to, if I say big omega, I can write anything here that is equal to Fn or less than Fn. In case of big O, it was equal to or greater than. Now it is equal to or less than. Okay. Now here, let's say I'm going to uh, check this. Let's say I'm saying that n square equal to big omega of n square. Is it true? Yes, it's true. Because this term is equal to n square. It can be equal or less. Okay. So big omega of n. Is it true? N square equal to big omega of n. Yes, it is also true. But can I write n square equal to big omega of n cube? No, it is not true. Because here n cube is neither equal to n square nor less than. So this is the concept of finding lower bound, that is denoted by big omega. Now let's move into the next one, that is theta, that we call tight bound. Okay. Sometimes it is very difficult to find out the tight bound. That's why we always prefer going with the big O, upper bound. Okay, so it is here the theta asymptotic notation. It is sandwiched between two things, like one is C1 into Gn and the other is C2 into Gn. If you closely observe this part, see any constant C1 into Gn less or equal than Fn, this is nothing but big omega. Now this part Fn less or equal than C2 into Gn, this looks like what? Big O. Yes. So means in case of tight bound, the function Fn grows same as Gn. Here you can see, okay, Fn is sandwiched between C1 into Gn and C2 into Gn. Okay. So if this is satisfied, then we can say that Fn is equal to theta Gn. Now let's find that tight bound for Fn equal to 3n square plus 2n plus 3. Okay. So if I want to find out the tight bound for 3n square plus 2n plus 3, what I need to do is that any constant C1 into Gn, let's say I'm going to write 1. How I am selecting these values? These are trial and error. You see, you will choose the value and then you will check the equation, and then if that satisfies, then you can write the tight bound. Okay, so always go with the definition. So let's say I'm writing 1 into the highest order term. Let's say I'm going to select for Gn. Okay, here you see, here also Gn, here also Gn. Do not make mistakes like G1, G2 like that. No, it is Gn, right? So 1 into n square is less or equal than 3n square plus 2n plus 3 is less or equal than, here if I write, if I write 8n square, okay, it will be true for all value of n greater than equal to 1. Yes, you put the value of 1, you will see that this is going to be true. N equal to 2, then also it will be true. Means for all values of n greater than equal to 1, this is going to be true. Now what is the value of C1? C1 is nothing but 1. What is Gn? Gn is n square. So this is our given Fn. Yes, this is our given Fn. Now here what is C2? C2 is 8. Here also Gn. So it should be same as that part. So here also it is Gn, n square. Here also it is n square. So you see, so in this case we can say what? We can say C1 into Gn is less or equal than Fn is less or equal than C2 into Gn. So we can write f of n is equal to theta of Gn. Now what is Fn? Fn is given to us, that is 3n square plus 2n plus 3, that is equal to theta Gn. So Gn we found as n square. So here we can write n square. Okay. So this is theta n square. So we can express 3n square plus 2n plus 3 is equal to theta n square. So this is how we find the tight bound for a given function. That function can represent time or space complexity. That doesn't matter when if we want to express in terms of asymptotic notation, then we can write in this way. So these are the concepts from asymptotic analysis. Okay. So here one important point here, as we have seen in the earlier two cases also. So Fn is equal to, if I say theta, then I can only write the term that is equal to Fn. I cannot write anything here. So here you see, if I say n equal to theta n, is it true? Yes, it is true, and it is the only correct thing. Like I cannot write n equal to theta of something else here, theta of log n or n square or whatever. Those all will be wrong, because this thing should be equal to Fn in case of tight bound. That's why it is tight, right? So when we can express or when we can find out both big O and big omega, then we express in terms of theta, that is tight bound. But always we prefer to find out big O. Okay, that is the upper bound. So we'll discuss two more asymptotic notation in the next lecture. Those are little o and little omega. Thank you.